So we're going to be talking about light clients and bridges, and something that I think is actually, there's a lot of misconceptions about what, especially with bridges, like how they actually work, and there's a lot of like media coverage about bridges, which I think is like actually kind of inaccurate, and then maybe some bridges which are like super popular, which actually suck when it comes to security. But like they're, the right people use them, right? So then they think it's really good, and then they get hacked, and it's fun. So we'll talk about all that. And I also work on like some bridging at Web3 Foundation. So it's something that's interesting to me. It presents a lot of challenges. So we'll talk about that. But first, light clients, the reason why we start here is because in the ideal world, we use them for various things, including bridges. So yeah, we kind of start here. This is a person who's working on a very popular light client for Polkadot. He also did a lot of the networking stuff, and he's quite known in the ecosystem and in the Rust community as well. His name is Tomaka, or Pierre. So it's a client but light. Yeah, I like that one, Joshi. So any errors in the slides, just like yesterday when Joshi did like the accounts versus UTXOs, he blamed me because those are my slides. Now these are his slides, so now I'm going to blame him. Except for I did add a couple, so there's no errors there. Cool. So yeah, running a node is hard. So ideally you guys just ran your own nodes, right? And in the ideal world, everyone would do that. Yeah. And the reality is actually, not everybody does it for some various reasons. So here are 3 reasons. Yeah, it takes up resources. We have limited compute in the world, right? And some people don't want to commit the compute resources they have to that. It takes some know-how. I would argue in some cases not that much know-how. Like if we could figure out technology today, we could figure out that, but it's my opinion. And yeah, I don't need it all the time is kind of something that's echoed a little bit, right? Like I don't need it all the time unless I'm mining and get money. But we'll see some counters to that argument a little bit. Okay. RPC nodes. So yeah, I guess first just introing these RPC node things. So we talked in the P2P lecture, and we've talked a lot about like you being on the network, right? Hearing other people gossip stuff to you. Being able to validate and verify what fork you're on and stuff like that. That requires you to be involved in the P2P network. And a lot of people are like, well, I don't want to run my own node or whatever, and I don't want to be involved in the P2P network. So they just say, you join the P2P network and just tell me stuff about it, right? And that's probably what a lot of people in here have used for checking balances on blockchains and doing different things with blockchains. So there's, this is like one RPC provider that will basically say, you connect to us and we'll just tell you what's going on the P2P network. But they can do stuff, right? Like they can just like see what you're doing. For instance, spy on you, we're in a certain country right now. So they could also censor you. That sucks, right? You're like trying to get something out to the P2P network and talk to nodes. But they could just say like, yeah, for instance, if the government, these are usually entities, right? And Fear is an entity that runs these big kind of gateways to the P2P network. So if I'm a government and I really don't like this blockchain, this P2P network group, I can just go to Fear and say, please shut this down, or please censor Joshi because he sucks. And they have to capitulate. They're a company at the end of the day. So that's not so good. They could also lie to you. So just like basically tell you faulty information. That's not so good. This is a nice one. So steal your boyfriend or girlfriend or whatever friend. 2024 now. So yeah. So I would argue maybe not the best thing, but they're convenient, right? and we all kind of like convenience. So is like, the question really is like what we're leading up to, is there a better way that we can all kind of be involved in the P2P network, but not have to go through this kind of service and still have things be easy? Because we like things that are easy. Any questions so far? Good, okay, great. Okay, so yeah, for resource constrained systems, these are some example, right? Like you have a phone, you are doing something on a microcontroller or running some code inside of a web browser. These light client things are kind of trying to address some of these particular scenarios where it's expensive to, this is kind of going back to the resource aspect, right? Running a full node inside a very, very small, not very computationally available machine is difficult, right? So we need something that's just like lighter and more able to do that. Okay. So what are some duties of light clients? And we could talk about like what it does, right? So we talked about, you guys were all going and, when you start from some point, the chain's been going and you want to join the chain, like you need some ability to sync the chain, right? So light clients typically don't like just sync the full chain. That would be very hard to just spin up, because one thing is like, I'm gonna pay some bill, right? And my stuff's offline. I don't wanna have to like spin up, like at dinner waiting to pay. I need to sync the chain, which in some cases, some of these blockchains can take like days on certain machines, and then be like, don't worry, waiter, I'm gonna get you, but I gotta sync the chain. That doesn't really work. So we kind of gotta be wary of syncing. Execute blocks, so this is like verifying the state machine again, right? We wanna take the original state, execute a bunch of transactions on it, and get the new state. That's kind of what we're doing in the syncing aspect. But what we do is we sync the headers. So for the devs in your assignment and in the blockchain from scratch, we notice that there's useful information in headers, and we can exploit that, or I don't know, that friendlier term, we can utilize that in order to achieve some kind of guarantees about what we're doing. I have this question because originally it was a question, and now I know the answer, so now maybe I can quiz you guys. What do you guys think of light clients that's trying to be fast and stuff? Like, would it need to maintain the transaction pool? We talked about the mempool. Does anyone have an idea, like what, like a strong argument for one or the other? Oh, Mauricio. Oh, yeah, Mauricio. But you were late, Irvin. Oh, okay. Well, I'll get you after Mauricio.
It was a layup. Yeah, I mean, I think either or case could be made, but I think if you're making the case against it, like the mempool is really used to essentially select transactions, which we use to create a block. And since light clients are not performing that, then perhaps there's no need. But I have looked into research that talks about essentially selecting the transactions and relaying them, but I don't think that's much talked about.
So, okay, yeah. So for those who didn't get that, like, we use the transaction pool to build new blocks. And these light clients, we're not trying to be like a full consensus participant in author blocks. We're trying to like interact with the P2P network in a very light but verifiable way. So his argument is, well, why do we need the transaction pool then? Anybody else have a conflicting view? I'm curious. Sure.
Yeah, I get that. Like, you are not building blocks with the light client, so you don't need the transaction pool. But then, when you are interacting with the blockchain and you want to send a transaction, does the light client like send it to another node that builds the transaction, and you are like going through another peer either way, right?
You're saying that I'm running the light client and I want to submit a transaction. Yeah. So should I maintain the pool? I mean, you're not going to build the block, but you're going to submit the transaction to the network. So, I mean, perhaps if you're listening to all the transactions coming in, you could you could know that yours should be in there, but you know it should be in there anyways because you sent it, right? But this is more about knowing about all the transactions, I guess. Which may, there's an argument. I mean, this is just a design decision, so I'm just curious what you guys think. Is there any last one before I move on? Okay, moving on. Checks consensus. So this is an important one. So if I'm just, this is actually one of the most important ones, especially for bridges. So one important thing is, remember, the consensus is like a viewpoint that we can see that a majority of the participants have. In the forking activity, it was like, which fork were you really building on, right? If you don't have a viewpoint into this, then you kind of have to assume that whoever's telling you stuff is telling you what most people are thinking. And that's kind of a trust assumption that maybe we don't want to have in certain instances. We want to have more guarantees of being able to view what people think in the network. That makes sense. We'll see a lot more of that. Maintain state. So like all the data, right? That's one of our resource constraints for these light clients. Like we want it to be light, right? And if you maintain all of the state, then that's certainly not light. Okay. Trustless. So we want these things to not be trusted. So what can we use? What's in our toolbox in order to make them not trusted? This is a picture from the Bitcoin white paper, like the simple payment verification. So it's basically saying that if you remember from your blockchain from scratch, I believe in one of the blocks they have an extrinsics root. Is that correct, Josh? Yeah. So this is like an extrinsics root that goes in the block header. So it doesn't necessarily need to trust that some transaction has been committed to in a particular block. It doesn't give you an actual state root, which you could generate an actual state proof for. And when I say that, maybe I just want to clarify that now. When I say state proof, can somebody like tell me what that means? Or storage proof? This is a good one. Okay, yeah.
Do you maybe mean that something is actually contained within the state, and then I have to just submit a Merkle proof with the data that adds up to the Merkle root, so I can prove to you that it actually is within the state?
Correct. So we talked about the Merkle trees before. We talked about what the Merkle tree represented. And in the hash-based data structures thing, we did this thing where we climbed up the tree and we got the root. That generally is what we classify as the state root again. And so a storage proof or a state proof would say like, maybe my balance is 100 and I want to prove that my balance is 100 in this particular block to you. So you have a state root and I can generate the proof that you can compare against with the current state root that you have to say that, okay, my balance is indeed 100, right? And so in many applications that's useful because I know that your balance is actually 100. Yeah.
Just from the way that the system works, I'm just trying to understand here. I know that there's the proof of the state. I understood that from Josh's presentation. In terms of the smart contract, so execute, pay X if X happens on this event, the smart contract, where does that sit?
Okay, so I think you're saying like, where does the transaction live?
No, I know the transaction is, I think.
There's no smart
Yeah, where does
contract
that
here, I'll
live?
just say.
Why? Isn't that?
There's like a script in Bitcoin. It's not really the same as a smart contract, which, by the way, there's a whole section for smart contracts. But so what was the question again? Sorry.
Like, maybe just in the blockchain, I understand that they're just the proofs of the states that have happened beforehand, and there's the hash to go back into the history, but I just didn't understand where the execute part happens.
When you actually, okay, so you have some transactions and you execute them on the current state. You didn't get that part?
No.
Okay, good.
Do you
So I think I can break it down really simply. Is that we have some I'm just going to I always do the money example. Sorry. There's other examples, but I have money 100 and you send me 10. That's a transaction. You sending me 10. And my current money is 100. So when you send me 10, I have now 110, right? So that's the executing of your transaction on the current state. My current balance was 100. You sent me 10, which is the transaction. Of course, I need to verify that you can send me 10 and that these things go right. That's your state transition function, like executing and checking that logic. But yeah, that's essentially it in a more application specific way.
Yeah.
Oh, no.
Yeah, I'm gonna ask.
Huh? What was that?
No, she was asking me if I could.
You have a
clarify
question?
Yeah.
Sure.
No, so she was discussing if I could clarify her question, but her question was more, I think, what she meant was that when you look at the blockchain, right, you have the state of the accounts, and then she's asking also, well, what about the state of a smart contract? So.
Oh, okay.
Yeah. So
I would wait
where
for
is
that. I would wait
Yeah.
for that. I would wait for that. The smart contract is kind of an account at the end of the day. But they'll get into that, I'm sure.
I have a question.
Oh, sure.
Yeah. Do light clients in a way like put constraint on the network? Like they have to connect to, I assume, full nodes, and they would constantly query those nodes for these Merkle proofs. So why would a full node want to be connected to a light client?
I mean, that's a good question. Like, why would it want to produce any proofs and
Yeah,
give anything
yeah.
to? I mean, it's kind of almost like that's almost like why run a node in a way. So, like, you're basically saying like, I don't want to talk to anybody else. I'm just going to talk to myself and do my own thing. Like that, you're perfectly valid to do that. But yeah, I think it's more like that gets into more like why run a node. Like incentives need to be aligned, obviously. But if like what's the, I guess when we just think of querying nodes like RPCs and stuff like that, like what's the incentive of getting the data even or providing the data?
Yeah, but the full nodes are also like producers and consumers, and the light clients are just consumers of the network.
Well, they submit. I mean, if you want to go down that rabbit hole, I mean, a lot of times they're going to be submitting transactions. You'd say the full nodes maybe are consensus nodes, which actually make money off of the transactions coming in. So I would think, in that way, I think incentives are aligned.
Okay.
Yeah.
Thanks.
I know those like leeches, right? Okay, syncing strategies. So, anyways. Syncing strategies. So we talked about this syncing thing being an issue, and we don't want to just like spend 2 hours waiting or days waiting for a full sync. And so there's ways to kind of do faster sync. So you could just sync maybe the headers of the chain instead of like the full state or doing the full like execution of every block. There's warp sync, actually checkpoints in the code. So this is one like where there's, yeah, I'm not gonna go into this strategy. I guess I'll just skip down to warp sync. So in warp sync, you maybe, the way that it works, at least in Polkadot, is that maybe we don't sync every block and execute every block, but we just check the validator changes, right? So like who's the current authorities for this period of time? And then when it comes to a new authority set, we also validate that these are the new authorities. So that when you get to the very end of the chain, you know who the authorities are, and you can kind of follow the tip that way. That allows you to basically just kind of, if you see like the whole history of syncing, you can kind of just skip to different parts of it. So these all have trade-offs, right? Like obviously, if you want to have the most security, you go through and you execute every block from Genesis up to the latest one. But maybe for your application or your use case, you're okay to like not go through this much hassle because maybe you're just going to read something, and if there's a little bit of an error, it's not a huge deal. So it all depends on the security of the application, the requirements of the security application. Yeah. So we can sync faster. There's some different techniques. Okay, so basically, at the end of the day, what the moral of the story is that staying inside of the gossip protocol or the P2P network allows you for the most security for your application. You're able to be tricked less or lied to or censored less. So we like light clients for that reason, in general. Okay. Bridges. So what are bridges? Essentially, you have two different consensus systems. We've talked about like from the viewpoint of, oh, sure, go ahead. William, Talis William here.
Yeah. I have a question. You know, we talk about all of the parties in the ecosystem, and it's very important to get the incentives right so that everybody can contribute security, and then I guess overall, you know, we have this. But I'm wondering, again, maybe to follow on the question of the light clients being the leeches of the network potentially.
It's funny because Talisman uses light client.
We will.
Disclosure.
Should there be an incentive that's given to run light clients then? Right? Because I don't think that there is today.
I think that's all within the scope of what the community should decide. In my opinion, and I think several others, you get a lot for having light clients be available. It allows for more transaction volume and more users of the network. So in my opinion, it's good. But and if there should be an economic incentive to try to boost that, I think that's all within the realm of possibility, and you know, something that the community should decide on. Yeah. Cool. Okay, so bridges. So we've talked a lot about a blockchain, and you went through forking a single blockchain. But it's like, what happens if I want to send some message to another blockchain? Maybe I want to tell something about my state in this blockchain over to that blockchain on the right. How do you do that? That's why we need bridges. Like, this is the whole kind of premise. And it seems like pretty simple, right? You're like, well, just send a message, right? And do something. But it's actually much more complicated because this chain over here, we talked about hard forks, soft forks. What are the differences, right? We have rules for the consensus systems. So the question is really like, well, how do we send a message from this blockchain, maybe about a transaction that CAT's balance is 100, over to this blockchain, when this blockchain might have a completely different mechanism for agreeing on a transaction or a block than this one. So that's kind of the problem that you run into, is that there's different rules for the blockchains. And so communicating to another blockchain that a transaction is valid or a certain person has a certain balance is kind of the goal, but tricky. So we'll talk a little bit about it. So there's these terms. I'm not a huge fan of the terms, but I do get them. But I like to think of it as, so this is like source chain and target chain. I like to say sender and receiver. Yeah, so it's important to distinguish these because the security implications are actually on one side, and we'll kind of see why. We talk about these things as like one directional at first. It's easier to think of it that way. So in this case, this chain is going to be sending message over to the target chain, and the target chain will react. And if it's a two-way bridge, like you can go back and forth with communication, then you just say that this is now the source chain and this is the target chain. But they have their own mechanisms for operating, and we'll show some examples a little bit. Okay, how are we doing on time? Pretty good. Okay, so we talked a bit about reorgs, or having one view of the chain, and then all of a sudden we realize that we have a different view of the chain based on our fork choice heuristic. So that's one thing that's super important about bridges, or a security implication in bridges. If I get told about the wrong fork, and I do something about that, and then we get a reorg, now I have a double spend, right? Because now I've acted on something like it's basically the same thing as the car example. You know, I've now given the car to somebody and they drove off, and actually they didn't actually pay me. So this is something that you have to take into consideration with when building the bridges, is this reorg thing and who you're listening to. That's important. M for message, basically. By the way. So in I'm saying reorgs because generally we talk about reorgs in terms of like proof of stake chains in general. I mean, I don't want to introduce finality because that's Joshua will talk about that. But in a proof of work chain, though, like how do we deal with like in a proof of work chain? There's a ton of forks, right? We just went through an activity. So if I'm another chain trying to follow, like say I'm this chain and I'm trying to get messages from this chain, which fork do I actually follow? Like, what do you do? Like, what do you think might be a strategy, actually? Kind of a naive strategy. Okay, someone said wait. Yeah, just wait. That's a lot of times what happens in general with blockchain when you're kind of unsure is like, especially proof of work chains. If you noticed when you first started that forking thing, it was like 3 forks, and it was like, which one do we even choose and follow? But then eventually, with some time, you guys all kind of settled on the same chain. And so if we just wait a period of time, then we can see that, okay, we're on the long, if we go certain distance back, it's agreed upon by most because they've built, I don't know, 10 blocks on it, for instance, or 11 blocks. But that's all kind of arbitrary, and you have to know how to choose it based off metrics or heuristics. Okay, so this is an important thing. So when we think of security, who is really at risk of the bridge model? I think this is helpful to think about because, yeah. So the sender chain operates as normal and its state machine is safe. So if I just send you messages about Bitcoin, for instance, and you do something wrong based off that, like, does Bitcoin care? Like, not really, actually. Nothing has happened. So it's usually the receiver that has some worry, right? They have to act accordingly. And the sender chain can kind of just be agnostic. So that's why when people build all these bridges from Ethereum or they build bridges from Bitcoin or whatever, these ecosystems, like the actual like ecosystems and the people who operate these networks don't really have so much of an issue usually. Yeah. So it's the receiver who has to kind of be careful. Okay, I just said that. Okay, so what do we need to validate and prove with regards to bridges? Oh, sure.
Here.
Right behind you.
I was looking the wrong way. Who's building then those bridges? I mean, what's the purpose then to build those bridges? Because I see that the receiver could have a problem. So who's building then those bridges? Is it the sender? Is it the receiver? Is it somewhere in the middle? Who is doing that?
Well, that all depends. I think I'll give you some answers to why somebody would want a bridge. But you know, there's many reasons. But who builds it is, well, so let's say people want to have the ability to replicate some aspect of Bitcoin on their chain, right? Their chain sucks. And maybe they're just a fork of another chain, right? There's like a bunch of these shill people out there. And so it's like they want to be able to get kind of leech off of one ecosystem into their own. They kind of have this crappy one. So it's like, maybe it's nice if I can act on some of, because maybe this one chain has a lot of activity, it has good security. I want to have a way for people to send account balance transfers on my chain because I say, ooh, it's more scalable or whatever. These are some reasons. So who does it? Maybe it's someone from the ecosystem of the receiver, generally, wants or they want to be able to act on the other chain from their chain. So it could be from either, to be honest, or even an independent organization. Even I think this one big one, Wormhole, they don't basically, okay, so in that case, there's this one, I guess, Wormhole, and we'll talk about how it works. It's not the greatest security model. Is one of the big hedge funds needed to be able to move an asset from this chain to that chain and kind of move around. So they built their own bridge because it was actually something that they wanted to use to improve their trading infrastructure. So they basically built it themselves for themselves. So it could be anybody. Is there another hand? Okay. Good. Okay, so what do we need to validate? What do we need to prove? So execution of the sender state machine. So we need to kind of see that the STF was executed correctly. That's something that's important. So this is regard to Merkle proofs and state proofs. This is one thing that we need to validate and also prove. Data availability. This hasn't even really been talked about yet, but it's a huge thing in blockchain. Who's going to provide the actual state data or the transaction data? Where do we get that? I think, I forgot your name, Luca. Luca mentioned, what's the incentive? That's a good question. At the end of the day, this stuff needs to be stored somewhere. It can't just be all stored in state. And who's going to provide that for us? We need to prove consensus agreement on transactions and or blocks, because a block is a list of transactions. We need to prove and verify that. If you send me a block and say, hey, this has got Andrew's balance in it of 100, just go ahead, but nobody else has agreed upon that, that's a huge issue. And transaction ordering. Yeah, I mean, in a block, the transactions are ordered in a particular manner, but on a lot of, I guess, a lot of these bridge type conversations, people focus on the transactions and don't say blocks a lot of times, but blocks are lists of transactions. But ordering, sometimes you have to order transactions in a particular way before you execute them. And so ordering does matter. Okay, some bridge models. So what we want is the right, obviously, but there's actually many bridge models that just used this kind of trust-based intermediary. So a very naive bridge, which I guess we'll talk about relayers, I think, soon. But a very naive bridge is, I stand in the middle of both blockchains, Andrew, and blockchain A sends me something, and I don't know, I lock up some money somewhere. And then I sign, Andrew, a transaction on the receiver chain saying, I have this, don't worry. And you do something based on that. I think hopefully we can see that that's kind of an issue, right? I'm kind of a very easy single point of failure. And there's been a lot of bridges that actually operate this way because it's relatively easy to implement. It's not a very complicated protocol. Trust this guy. And from cryptography, all we really use is a few signatures, right? I sign something, Andrew, I see it as Andrew, and then I send another signature to the other chain saying, yep, I got it. So these are generally pretty bad, but actually in practice, way more than you think. I would say if you're going to use a bridge, please research it as much as you can. It's not as sound usually as you think. Trustless would mean that we could actually prove stuff about the other blockchain on say on the receiver chain from the sender chain, and that would be nice if I can get strong guarantees about the other chain instead of trusting just me, Andrew, with the signature. Okay, what are some ways to do the trustless bridge design? So the most we talked about what's the ideal case, right? Is that if we want to interact with a blockchain, we run our own node, and we don't just trust these other intermediaries. So this is kind of one of the design points. This is not just true for you and me. This is actually true for blockchains themselves. If a blockchain could run a full node of the other blockchain, that's pretty good, right? Like it's able to get a lot of guarantees and be partaking in that other consensus system, and it's ideal because when we are a participant, a full node in the other consensus system, we have strong guarantees about what everyone's thinking. But we can't just run a full node of every blockchain, right? Running a full node is expensive, and if we had like literally every chain running every other chain's full node, that wouldn't work. It's not really scalable. And so if I'm on the receiver chain or the target chain, I can run a light node. I can run a light client of the sender chain, and then I can use that light client to give me proofs. And I'll show what that looks like. So yay for light clients to help bridges. More secure bridges. Okay, so this is like just an example of a BTC relay. So you have so this relayer, I guess I didn't really define what a relayer is, but essentially you have some off-chain code that does some stuff based off what's happening on both chains and submits messages or transactions to one chain or the other. Maybe it gets a storage proof from chain A and it submits the storage proof to chain B, which has some way to verify it. So these relayers are kind of like these intermediary things. And one good question, maybe that builds off Luca's, is like, how do you incentivize those people to run off-chain processes or relayers? And that's another thing where we kind of use economics a lot of times in order to pay them to do stuff. So in this example, you have some relayers submitting Bitcoin block headers. And this is useful for your contracts module, I'll just say. A Bitcoin transaction is submitted to be verified and a small fee is paid. So again, we're talking about how do we incentivize these people to do stuff. And if we kind of think back to the simple payment verification thing, we could have some way to verify transactions have been committed to inside of a Merkle tree in Bitcoin. And then the verified Bitcoin transaction can get sent over to, like, for instance, a smart contract on Ethereum. And so the smart contract on Ethereum can then just mint some new coin, right? Wrapped BTC. So, yeah, just a nice little diagram for how that works. Okay, so design challenges. I guess I've been hinting at this the whole time. This is a great slide, though. I don't know where this is from. If anybody does, just let me know. Well, not a great slide. Hopefully no one got hurt. So, how can we peer without networking? So yeah, peers. So I guess I just introduced the relayer, but a permissionless and trustless role. So hopefully, if you're not relying on the relayer to literally be a signed single entity, then if it's using light clients, then it can be this kind of outside third party, which allows the chains to communicate more efficiently. So if you have one relayer, probably not so good, right? So for instance, the Polkadot Ethereum bridge, there's this, it's not going to be, like, you usually have your security model rely on at least one honest relayer, because if everybody's just lying to you always, like, one thing that Josh is going to talk about in his next one, which I won't stomp on, is we have to have some assumptions when we're talking about these systems. And we always have some baseline assumption that we have for security. And generally with bridges, you have at least this assumption, which is that at least there's going to be one honest party. And we'll see in consensus systems later that there's other assumptions that are built in as well. Any questions? I should tell a joke or something, right? It's time for a joke? I don't know any, sorry. I just want to get done, eat my food. Okay. So this is a nice, yeah. So everyone's all excited with all these light clients, and we can submit all these storage proofs and state proofs, and then we forget about the fact that people are in it for the money, right? And they can collude and mess with networks. So what does that mean? I'm going to avoid finality in this conversation because Joshi will define it and talk about it. But what I will sum up is that if you, let's say consensus participants are in our blockchain, we're validators, we're producing blocks. One thing that we have in these consensus systems is if people misbehave, we punish them. And we talked about in proof of stake, basically that means like we take your money or something. In proof of work chain, it's like you're just wasting your time and energy, right? So given that fact, maybe I'm a nice, honest participant in my blockchain. I'm a validator. I do things correctly, right? But we have a bridge to the target chain, and the target chain depends on us telling it something, right? Telling it some information, giving some proof that this is what we're talking about. This is what's going on in this blockchain, in our blockchain. But even though we're being nice, honest, good people here in this blockchain, maybe we all want to collude together to trick that chain, right? So one thing that you have to keep in mind is even though I'm an honest participant here, if we all collude together and try to screw over what's going on this chain and the viewpoint that this chain has of us, this chain necessarily isn't participating in consensus on our chain, right? So they don't have a way of basically reporting back and saying like, oh, they've been mean to me, right? Oh, shoot. They've been mean to me. Get back at them. And then the other people are like, you're not even in consensus, bro. Like, what do you want? So it's important that this is a big security design challenge that we take into account. One of the many, but yeah. So what are so I think this will get defined in the next lecture, but we have this term in blockchain, equivocation. So it's when we basically, we say two conflicting pieces of information, right? It's like, I have $100, I tell that to somebody, and then I tell another person, I have $50. I mean, there's conflicting. I have to have one or the other of the balances, right? So one way to kind of deal with this is we add in a challenge period. So in a lot of these systems, these optimistic systems, optimistic rollups, we have these things called submission of fraud proofs or challenge periods of when somebody can say, those guys were bad, here's why they were bad, I have proof of it, punish them, please, and give me some money, usually. That's usually how it works. So we add in these spies in a lot of ways. We call, like in Polkadot, they define them as fishermen. And they basically check the activity and see what's going on. And if someone's being bad, they submit a fraud proof and they punish them and get some money. So, like little tattletales. Okay. So this is kind of a nice thing. So multi-chain apps. So here's the goal. Like we said, like, why do we even want to do this? Why do we want to build bridges? I think that's what, I think your name's Mario. Asked the question, like, what would we want to do? So perhaps we have an app built on all of the blockchains, can interact with all of the blockchains, and has some UI to the user, right? Like now you have this kind of pain point, right? Where it's like, I gotta go and I gotta interact with this app on Ethereum and then on this chain. And it's kind of this like little bit of a user headache, right? And we wanna make these applications easier for people to use so that they use them and our crypto goes up. So maybe that's my goal. And so how do we like, this is kind of what we want. And so, so if we have a header, we're using this, say we have a blockchain header. So an app user could submit some proof that they have some balance, they have some, they have something, right? There's some transaction has happened. So they can submit a kind of this like the Bitcoin picture that I picked, the simple payment verification style transaction proof. Hey, I've sent this message. I've submitted this transaction. Believe me. And then if you need some maybe source chain state in this app, right? You could submit a state proof from one of the chains, and you could verify it. So we could check balances. We could prove that I sent something to somebody at a particular time point. We can aggregate up all of these actions into one app and one UI. This is kind of the goal. But it's kind of a caveat. Security is so. Oh, that's the strong person and the weak person. Security is an issue. So if someone could think about, out of all the stuff we talked about today, say we have some application that has a bunch of blockchains which are bridged together, which it interacts with. What is the underlying security, like what's the weak point in all of that? I don't know if I'm asking that question right. Sure.
I don't know, the scenario could be that you have this bridge to one secure and strong chain, and then you trust some chain that is weak, and then if you, I don't know, wrap it your coin, you lose it. So
Right.
it's a dead chain.
Okay,
It's
so
not reverse.
right.
It just died.
So if all of the chains are bridged together, the weakest one is really the weakness of the whole system. This is kind of the issue. Because if all the chains have two-way bridges, remember we talked about where it's safe and where it's dangerous. If all of the chains have two-way bridges, then it means that the weakest consensus, all we need to break the whole system is for one consistent consensus system to basically fail in some way. And so if that happens, then the error just propagates everywhere, and we have basically an issue. So a few people have had opinions on this. I think Vitalik has an opinion on it too, that it's kind of a weak general security model. But perhaps, I don't know, maybe, this is kind of an open question. Maybe we only accept some blockchains which have proven their security of their consensus over time, right? There's different ways to kind of approach, is more philosophical of how we deal with this. But it would be great if we had these multi-chain apps, right? And here's just a kind of a small example. So I send some tokens to a contract on a particular chain. That chain the message is relayed using a relayer to some other destination chain. Here it says like this is kind of an off-chain relay. XCM, we're going to talk about this. This is a message format. Basically, just some way we get the message over to another chain, and then the new wrapped tokens are minted on the destination chain. Just as a simple example, you can maybe interact with one contract, and that one interaction you have with your user could just be propagated around a bunch of chains. Would be kind of nice. Any questions? Sure.
So what really happens with the original tokens on the original source chain? I mean, basically, like we have the if, for example, like I want to understand like the entire process, for example, for USDC on Ethereum, on Ethereum and Polkadot. Is this the way to look? It is a bridge, right? Some sort.
You're talking about USDC on
USDC, right?
on Ethereum?
On
And
Ethereum and Polkadot, right?
Yeah. So there is some main USDC state, and it's being managed somewhere and replicated. I don't know the exact implementation of USDC on Polkadot. That's
But then, what about the custody of the tokens on the source chain? How that's done for a user?
I mean, I guess I would say, so you have something that's getting interacted with. This is like some authority contract, and it sends a message saying, hey, Cat's got a balance of USDC of 100 to all the chains, right? But then you move some money on this other chain, right? and some message needs to get sent back to this. It basically needs to get propagated around, right, to everybody. So it it works like it's basically a lot of source chains and a lot of target chains need some way of syncing. Now, the easy way, right? This, like, we're talking about this ideal world, right? The easy way is all of the chains listen to some central server, which is actually managing your balance, and then that central server will actually just control all the logic, right? It'll update each one individually. But this kind of introduces this like centralization notion, right? But that's the easy way to do it. Exactly how, I don't know, I have to check it.
Yeah, maybe I could comment on that really quick for context.
Sure.
Yeah, there's like, it really depends on the implementation of the quote unquote bridge provider or token provider. So one thing that you see, for example, with USDC is that Wormhole has its own bridge to send over USDC from, chain A to chain B. And when you do that, you'll notice that it's called something like Wormhole USDC, right? But if you use quote unquote now native solution or solution from Circle, you'll get a wrapped USDC in the other chain. Now, essentially what is happening right now is that some chains have two variations of USDC, and the Wormhole one I encountered this like a few months ago. I used their bridge, and the liquidity pool was so low that it was worth like 80 cents or something, right? Versus the one that was done by Circle, its liquidity was like higher, right? Because more people were using that one than the Wormhole one. So it depends on the implementation.
So I will say that what I didn't mention is I talked about the scenario where you have source chain trusting Andrew and I'm talking to the target chain. That's one approach, like that, not so secure. But in that aspect, I need to basically hold the money, right? So that's why I'm very vulnerable to actually get exploited. In the case of Wormhole, I think all they do is they just guard that by a multisig. So there's like 10 Andrews that need, I don't know, I think there's 20 something Andrews or whoever that all basically need to sign a threshold in order to commit the transaction on another chain. Guardians, yeah, guardians, weak ass guardians. So I guess we'll take two more and then we go for lunch because we'll get out on time then. Yeah.
So,
Okay. 3 more, 4 more. Sorry. Okay. All right.
did
3
I
more.
win the consensus algorithm? Can I go?
Yeah.
So, having worked on fintech and stuff, if we, let's say, even healthcare, these systems evolved to include HIPAA compliance and then PCI compliance and stuff like that, like payment cash industry compliance and healthcare compliances, everything for the systems that are in those domains, right? So what I'm trying to say is there like maybe this is a suggestion or a question, like Intel has SSEs for their chips, secure extensions, and trusted, like everything we are talking about is security, right? So in trustless environment. So is there like a standard that every chain has to comply with, or we should come up with a standard that they have to comply with, and then it's all good?
Oh, are you talking about, okay, so a standard for how these bridges should work, for instance?
Standard for how these blockchains should comply to a security.
Yeah, okay, good question. So there's a few people who have opinions on this. I think there's some protocols which want to become the standard way to bridge, basically. I think I forgot the name of it. Layer 0 is trying to do something like this. Kind of a weak protocol too. Sorry not to bash them, but some people are trying to do this, but then you have to basically get each ecosystem, which ecosystems already have internal fighting. You probably noticed that in ecosystems, especially like Bitcoin and stuff. And so getting them to then comply to a standard amongst all of them, it's a little bit of a challenge. But yeah, thanks. Next question.
I don't know who to give it to.
I think it was Jessa. You had your hand up.
I did, but
Okay.
it's actually for Irvin. My question is like, does it depend on the user approach that had that 80 cents versus 100 in the liquidity pool, or is it like the lack of liquidity available on that?
Okay, offline discussion.
Oh, fine.
Thanks. And then Vincent. I think that's your name, right? I hope it's your name. Ryan. Oh shoot, I'm so sorry. That's not even close.
It's working now? Okay. So in a truly trustless bridge, is there like an emergency shutdown function?
Oh, nice question. Depends, but there's some people who do have those, right? Yeah,
Because
they do
one
exist.
chain gets hacked, it's like,
They do exist.
can
They
I
do
get
exist.
rid of this chain?
Right, and this is we haven't talked a lot about this like governance stuff, but in blockchains we there's governance is used to kind of have a kill switch in a lot of ways when there's things that go wrong. And governance could be like what most of the miners agree on, which in the case of like the DAO hack, or it could be like some actual on-chain governance like Polkadot. Last one, and then we go to lunch. Probably some announcement.
So can you go back to the slides? What does the SPV style proof means? I mean, I think it's before the gym guy. It's before the guy is doing dumbbell. So you just go up.
This one?
No. SPV style proof. It's very close to the end. You just
Okay,
go close to
before
end.
the guy.
Before the guy.
Okay, it's probably okay.
No. It's go up and down, I guess.
Okay, you can just come up and I'll answer it
So
offline.
what's the SPV style proof? What does the SPV mean?
Okay, so I did want to go back to it, but it essentially is proving a transaction has been committed to inside of a Merkle tree.
Is it short for?
Simple payment verification.
Okay.
Yeah. So you don't get to the actual state proof. You just get proof that someone actually committed to send this transaction. So, anyways. Okay.